right, we'll get started then. Hey, what's up, Flav? I just saw you're here too. Just so you know, Flav, you're up at the end. You'll be bringing it home today. But yeah, welcome everybody to the Argo Workflows and Events Community Meeting. Thanks for joining. We have agenda today, a few announcements to kick things off, and then we have 2 presentations, updates on projects related to the Argo ecosystem. So I'm excited to get those updates from Jam and Derek and Flav. So we'll let folks join as we're continuing the announcements here. I wanted to make sure everybody could see that the ArgoCon schedule is announced. So if you go to the link in the Google Doc, and by the way, thanks everybody for putting your names in. You'll be able to see who's speaking. Looks like there's 2 tracks, so 2 rooms. So one for Argo CD and one for Argo Workflows, and I think Argo Rollouts as well. And then there's a good amount of lightning talks as well. So we hope to see you all in person if possible in Europe, but understand that's not always easy. So we'll catch you online if not. And that is that. I guess one thing to note is the in-person event is sold out. So if you don't have tickets, DM me and I might be able to help you. But if you want to go, good luck. We'll figure something out. Yeah, next announcement here is we have added to the Killer Coda course. This is a free intro to Argo Workflows course. So if anyone's new on your team or you're looking to refresh on the latest Argo Workflows, we added a module here about using Helm to install and manage Argo Workflows. And then we also added a module that's pretty handy to run all of the examples that are on the open source repo. So everything there is pulled in into here and can be ran in the browser. So that's a nice way to, quickly try a new example if you don't have everything set up locally already. And next, quick announcement, just a couple of shout outs to folks here. Yeah, we've had some new contributors. So just want to give a shout out to Sandeep for this quick fix he put in. So nice work. Even a 1-line change is welcome. So much appreciated. It's a great way to get started. I think Sandeep also was able to use code spaces on GitHub to run workflows. So that's something we'll be trying to document a bit better for more folks to use getting started in developing. I think Alex Collins worked a bit on getting that set up. So shout out to Sandeep and Alex on that front. Shout out to Yao. I think you're on the call too. Hi, Yao. Welcome and congrats on your first PR. This was a great fix. And yeah, excited to work with you more. Do let us know if there's other PRs you're interested in working on. So yeah, quick round of applause for Yao, who actually is on the meeting.
Thank you.
Yeah, you're welcome. Another shout out for a config Mac fix that got done. I think this might have been a regression. So thank you, John, for hopping on that and putting that fix in. So the core teams didn't have to. And a shout out for another, I think it was a quick regression in 3.5 that got fixed really fast thanks to Petri. So yeah, this was also Petri's first contribution. So high five, thank you for putting that UI fix in. And one last shout out to Isatha for getting a couple of longstanding bugs closed out. Great to see these. So yeah, thanks everybody who's contributing. If you are looking to put in your first fix, just let us know. Open up an issue on the repo, a mentorship with the mentorship label, and we'll circle up with you and help you get your first PR going. You can also always DM me in Slack at Kalen, and I can point you to someone who might be able to help in the part of the code base that you're working on. All right, let's see. So from here, on the agenda, I'll hand it to JM for an Argo Helm update whenever you're ready.
Hey everybody, I'm JM Jason Meredith Foley, staff engineer at Procore. I've been a maintainer of the Argo Helm repo for a bit now with Marco Kilchfer. We are doing our best to make sure that the Argo Helm charts stay up to date with the upstream projects. It was pretty bad for a bit there. We got it fixed up. Now, I think the longest we've had is a day where we fall behind an upstream project. The biggest highlights right now, we're trying to get OCI formats released so we can have those available to consumers. We're also trying to update the documentation and the READMEs to make sure it's more easily consumed. And we're open to all PRs and feedbacks. We've opened up the discussions board on the GitHub repo now, so people can actually ask questions if they don't want it to be code related, more about process. And we're open to all feedback. We were originally trying to stay as much in sync with Customize as possible, but Helm has its own quirks. So we're trying to work those idiomatic philosophies in place. One of the most common ones is why are the CRDs inside the templates folder? It's because we want to be able to customize some of the annotations, and also the updates in Helm 3 are not very friendly if they're not in there. So yeah. Again, PRs are welcome. All feedback's welcome. Nobody's married to the code, but we do have room for improvement on some things. Anybody have any questions? And I know Kaylin and the Pipekit folks have been showing interest, like they added the killer coded thing for Argo Helm, and other stuff's potentially coming down the pipe. So as much exposure, if you have companies or friends that are using Helm and they need assistance. I've been trying to be very active on the Argo Helm charts Slack channel. And if you all see anything in your upstream channels that are Helm specific, please redirect them to Argo Helm charts. We kind of got to start redirecting folks so that y'all don't get overwhelmed with those questions. So cool.
Yeah, thank you for the lift with that on Slack, Jim.
Yeah, definitely.
Awesome. Yeah, any questions for Jim? Awesome. Yeah, thanks for the update. I don't know if there's a quick show of hands if anyone is using Argo Helm. Let us know. We'd love to see who's interested in getting involved there. But yeah, really great to see the project, sub-project keeping pace with all the other Argo projects. So thanks for the leadership on that, Jason, and team of folks all over the world maintaining Argo Helm.
Definitely glad to help.
Great. So yeah, next on the agenda was Derek Wang, and wanted to hand it to you for an update on Numaflow and Numaproj generally.
All right. Thanks, Kaylin. Thanks for Kaylin for inviting me. Yeah,
Sure.
we're a pleasure to be here. Let me share my screen. All right. Oh, sorry. No. Slideshow.
I always do that too.
Okay. So let me start with some self-introduction and the project background introduction. My name is Derek Wang, and I'm a software engineer working for Intuit. I'm also a project leader of Argo events. And in terms of this project, Numaflow, it's actually started like 15 months ago. And the reasons for that is like, so first of all, my team in Intuit is like platform analytics and observation. And from the name, you know that we're going to do a lot of real-time data processing and real-time data analytics, right? And so we were thinking about if there's a way to use a tool to do in-cluster data analytics without going, outside of the cluster to do some, external, which has some external dependency stuff. And internally, we use Argo Workflows a lot, but Argo Workflow, as you know, can use to do batch data processing, but it's not pretty good for like streaming data processing. So that's the reason we start this project, Numaflow. And so first of all, it's a parallel real-time data processing engine running on Kubernetes to do real-time to do streaming data processing. That's the overall definition for Numaflow. So features. First of all, it's a Kubernetes native. I mean, I don't need to mention too much on it. It's like if you know about Kubernetes and then you know how to use Numaflow, because we wrap the data processing jobs in Numaflow as a CRD. You just create a CRD object and then you get your data processing job running. And lightweight, and the Numaflow can be run in Kubernetes cluster. Also, we ever try to run Numaflow in a Raspberry Pi. It's pretty interesting. So, and next is like a language agnostic. So because a data processing job running with Numaflow is the actual Kubernetes pod, so you can write your data processing jobs with whatever language you want to use. And we claim to be exactly once semantics, and which means there's no data loss during the data processing with Numaflow. And we also support auto scaling out of the box without using any external pod auto scaling strategy. But if you want to use, for example, you want to use HPA, it's doable. And we also support, we have the watermark out of box support. The watermark step is used for aggregation type of data processing for a data processing pipeline. And we do like map reduce type of data processing. In terms of use cases, as I mentioned, internally Intuit, we do real-time data analytics, or we do like event-driven applications such as anomaly detection, monitoring, and alerting stuff. And yours can use Numaflow to do streaming data processing, like to do data instrument or data movement stuff. Yeah, skip the left part of why we build Numaflow. Just to look at the right logic diagram of the Numaflow pipeline. So for Numaflow, right now we support line or tree DAGs for data processing, but ideally we're going to support a diamond kind of DAGs as well, but it's not there yet. So from this diagram, you want to see we name it as pipeline, right? For each pipeline, we have each pipeline contains multiple. We call this nodes as vertex. So each pipeline contains multiple vertices. And there are 3 different types of vertices in a pipeline. From the color, you can tell. There's a source vertex, which is used to ingest data from the external data source. And there's some user-defined function vertex, and where you run your own data processing logic. And then after processing the data, you forward the data to some sink vertex. This sink vertex used to write the process data to a real data sink. Here, you can, from this diagram, you see the data will be written to Kafka or Pulsar, right? That's like the logical view. And here is a simple example to write a Numaflow pipeline and run it in a Kubernetes cluster as a spec. So you have we have a new CRD named pipeline, and you give a name. And there are 2 major sections in the spec. One is a vertices, where you define all your data processing nodes. So for example, here for this one, we have a vertex named in, and which is used to serve as HTTP endpoint to read the data, or you can, you give some other type of data source, like Kafka or any other type of source we support. And there's a processor vertex. It's a user-defined function, or we short name is like UDF. And you give your a container, which is a image you build to run the data processing logic. And after processing the data, and we have another vertex named out, which is used to write the data to another Kafka topic. And there's another section in this spec, it's called edge, which is used to define the relationship between those vertex. So for this one, it has 3 nodes, 3 vertices, right? And then the relation is like the flow is like from in to processor, and from processor to out. So that's a way to define a Numaflow pipeline as a CRD object. And moving forward, I'm gonna spend most of the time on the introduction about the data plane to see how it looks like after applying a pipeline spec into a Kubernetes cluster and how it works there for those data processing nodes. This is a high-level architecture of data plane. So, for example, just if we apply the spec as I just mentioned to your Kubernetes cluster, and our controller will generate some pods for each vertex. So, for example, this source, we'll generate some pods for it to use to process data, to read data from a data source, and similarly for UDF and sync. And there's one major piece I didn't mention till now, which is called interstep buffer, and short name is ISB. And in Numaflow, the communication between those vertices is not directly a call from a source to a UDF or from UDF to a sink here. So instead, we use something called ISB to transmit the data. So for example, for this source vertex, the pods read data from a data source. It write to ISB, which is a worker queue. It's a message queue, and then the next vertex will read data from the message queue and do some processing and write to the next message queue. And which means for each of the two vertices, there's a message queue sitting in between, used for data transmission. Okay, and the logic running in each type of vertex is similar, no matter it's a source, a UDF, or a sink. So they read data either from a data source or from ISB, and probably they're going to do some data processing for source. There's no data processing, but it's like do the skip that logic, and then you write to the next ISB or write to a data sink. And after that, you do acknowledgement on from your data source or from previous ISB. So we abstract this logic for each type of vertex, and that's a high-level data processing logic happening in Numaflow vertex path. Okay. And next is about the ISB. I mentioned the reason we want to have a ISB component sitting between every two vertex is we want to manage the whole process of data processing. We don't want to detect the back pressure. If we go back to the diagram, so data from this pipeline, the data move from the left to right, but it is possible that there's some back pressure happening. So, for example, for a sink, there's some pressure to write the data to a data sink, and then we need to get this kind of pressure passed to the previous vertex, so that we're going to do some strategy to slow down or either stop writing the data. So we need to detect this kind of back pressure, and with this ISB components in between, we fully manage those buffer the message. We can detect back pressure, and then we control all the flow. Also with this, we can achieve auto scaling stuff. So our auto scaling is actually based on one of the factors is the back pressure step, and that's the reason we want to introduce the back ISB component into the data processing platform. So actually, the ISB in its buffer, as I mentioned, is a worker queue. So technically, any message queue technology having this kind of a requirement can be used as an ISB. Today, we support Redis Stream and JetStream from NAS as into the buffer implementation. But as I mentioned, this ISB is a plugin. Technically, can use as long as you implement this kind of requirements, you can use it as ISB. Okay. This slide actually is used for a deep dive internally, so I'm going to skip some of the slides. This is, how the ISP worked internally. Skip this. And this one is the thing I just mentioned. What the logic happening in every vertex pass. We read from buffer or data source. We call UDF or not, and then forward to the next ISP or data sync, and then acknowledge, right? And we do a infinite loop in the vertex pass. And then we have some logic to control. So for example, before we acknowledge a message from a last buffer or data source, we will not read new data. So this makes sure all the message will be processed. And when we forward the data to next buffer or sync, we have some mechanisms to make sure the data will be only written once. And the whole logic here makes sure we achieve the exact once delivery guarantee. I'm going to skip this one as well. It's like, how to implement ISP stuff. That's something I just mentioned. How we achieve exactly once. Quickly go through it. And then next slide, so it's about the vertices we support today. As I mentioned, we support a source, user-defined function, and sinks. Okay. So first one, the source is quite, it's easy to understand. The source is like used to read data or ingest data from a data source. Technically, we should support any kinds of popular data source for Kafka, SQL, SS, but the SQL SS is not there yet, but it's easy to implement actually. And yeah, the source is quite straightforward. And one of the things in the roadmap is we will support user-defined source. So we're not going to support all the source, sources, but we will give you a chance or give you the capability to implement your own source, where we call like user-defined source, but it's not there yet. It's in our roadmap. And next part is about user-defined function vertex. Today, the user-defined function has two different kinds of processing. Like one is for map, one is a map, one is reduce. So map reduce is a common data processing approach in the data world. So for us, we do the similar things. So the UDF is actually applier. It's a user-defined function, and as a user, you use the user-defined function to process your own process the logic, process the data and apply your own logic for it. You can use whatever language you want to use in your user function. And this is a simple diagram about how a map type of user function works. So for the vertices, if it's a source and sink, the path generated for this two type of the vertex, there's only one container in the pod. But for a UDF, there are going to be like two containers. One is the main container, another one is a UDF container. The main container used to read data from ISP and also write data to the next ISP. And your user-defined function logic is actually running a different container. And the communication between these two containers is through gRPC over Unix domain socket. So here the UDF is a gRPC server, and the main container is a client. Today, for the map functions, the gRPC protocol we use is a unit recall, so which means you send a request and you get a response. And the logic here, as I mentioned, read from ISP, and then the main container read from ISP, and then send the data to the UDF container, you process data, get the response, and then write to the next ISP, and then you acknowledge the message in the last ISP. And this is a sample code. If you write this in Golang, if you write your own data processing logic in Golang, what the interface looks like. So you implement a function, whatever, and use a handle here, right? and then you're gonna get the data. The data, basically the data in all the data parameters like the key and a value. So you're gonna get the key of the data, and also you get another object named data. Within data, there's most important things. Data value is like a binary array. And in this example, what we do is like this user function just to do an even or odd process. If it's even, just send to you return a message with the key even, and with the data it's odd, return odd, right? So that you can do conditional forwarding stuff. And then use our SDK to start your the JPEG server, and then wrap it as a Docker image, and then put in in the spec. You get it wrong. We also support some built-in functions. So for example, some filter functions, you don't need to write your own UDF to process it. You just use some built-in functions. And so that's for map. And for reduce type of vertex, so reduce is like you want to do some windowing operations. So for example, you want to do do a sum every 1 minute, right? So it's like this is like a fixed windowing, or tumbling windowing, or you want to do some sliding window every 1 minute. You want to do aggregation based on the past 5 minutes, for example, right? That's a windowing strategy we support today, is like fixed or sliding. Or you can say, hey, I want to group by key. You want to do some aggregation based on country code, for example, and then you can do group by key. And also you want to do some shuffling. You want to do some parallel processing. For example, you have your throughput is very high. You want to do parallel processing with shuffling, and you can specify the parallel. For example, you want to do 5 concurrently, right? So you can do that. And there's something called PPQ we'll be introducing in the reduce operation. I'll explain here. So similarly for the reduce type of vertex, there are 2 containers running in the pod. There's main container read from the ISB similarly from to the map, but there's some difference here is after reading the data from the ISB, it's going to pass the data to a PBQ. The PBQ basically is a storage, local storage. Today we use PVC for it. So the data written, data read from the ISB will be stored in the local PVC and pass the data to the user-defined function. And then let's say you do like 1 minute window. After 1 minute, and we close the window, and you got the response from the user code, and then we write the data to next ISB, and then we clean up data in the PBQ. And sorry, I forgot mention the acknowledge. The acknowledge actually happens when you store the data in PBQ and send data to the user function, and then they acknowledge. So there's some processing logic difference from the map and data processing. And the reason we do that is, their aggregation operation is quite different from the map. So for map is you send one request, you get a response. But for reduce, it's like you send a bunch of data to the user function, and then you get one response. So here, we still use gRPC protocol over Unix domain socket to process the data between the 2 containers, but we use different mode. So here we use bidirectional streaming. So you send the data to the UDF container in a streaming fashion, and then after window closing, after closing the window, you got the response data in another stream. So there's some different there. And for the user interface, it will be a little bit different from the map. So here, what you get is you're gonna get 1 key, and then you're gonna get a channel which used to pass the data from the main container. And here, this example is like we do a sum, right? So you get the data, get all the data from the channel, and in the end, you write a response back. Yeah, that's a reduce operation. And next one is about syncs. Syncs, we support some native type of syncs, for example, Kafka, Logger, or any other popular data syncs, which we will support those kind of data sources natively. But we also provide some something called user-defined syncs, which means you can implement your own data writing logic. For example, you want to write the data to a database. That's something we will not support natively. So you can write your own logic for that. And the data process logic, similarly to the UDF, you read the data and then you pass the data to the UD sync container, and where you write your own logic to write the data to your data sync. And then you give the response to the main container and acknowledge the data. Okay. And the user interface will be something like this. You get a channel where you can get all the streaming data from the main container, and after processing, they give the response, say you have processed the data, and then return. And next is about auto scaling. As I mentioned earlier, we support auto scaling out of the box, and the auto scaling is based on several factors: pending messages, or we have ISP, so we depends on available buffer space and your processing rate, and also we'll consider is there any backup pressure. So for most type of vertex in Numaflow, we support auto scan out of the box, but there are some exceptions. For example, for HTTP type of source, we cannot do that because there's no pending message, right? But for those type of events or those type of vertex, you still can use HPA to do it. So we support HPA as well. You can use CPU or memory or whatever, or any other kinds of auto scaling auto scaling tools to do it. For example, use Hera to do it. Yeah. Briefly, mentioning that. And correctness. So the correctness is the most important thing for a data processing platform. So here, for our Numaflow, it's like there's some data out of order stuff. That's the reason we have multiple, for one vertex we start multiple paths. So out of order is a natural of data processing platform. And then with this kind of out of order, we still need to make sure the data is correct. So we have some we put a lot of effort on it. I'm not going to touch very deep on it. And the way we, I'm going to skip all of this. It's like the way we make sure the data is correct. Okay. And watermark, as I mentioned, watermarks are very, very important for data aggregation. Today, when you do windowing, no matter it's a fixed window or slider window, even you say I want to group by the key every 1 minute, but that 1 minute is actually not the processing time. It's like so the time is like a real event time based on real. For example, now it's 8 o'clock, or let's say 8:02. Okay, if I want to do like sum every 1 minute, so you cannot say, hey, now it's 8:02. We want to close the window from 8:01 to 8:02. Actually, the data you're processing probably is still 7:59, right? So there's some that's by natural. The data happened in the past. But when it goes to your data processing system, it's not, there's some delay. So we actually put a lot of effort on watermark propagation as well to make sure the data moving to the system have the watermark correctly calculated and propagated to all the downstream vertices. And we use a watermark to make sure there's no late data to close the window correctly. Okay. yeah, I'm not going to touch very deep on this as well. And next part is about control plane. I think I'm gonna use a very limited time to mention this, to introduce this, because I think everybody here are very familiar with the Kubernetes related application development. So the control plane design philosophy is we want to make it as light as possible, and we only want the control plane to do resource orchestration and management. It should not touch any data plane business logic. And if the control plane is down or temporarily unavailable, the existing data plane should still work, still be running without any issue. So that's the basic design philosophy for the control plane. And it's a high-level architecture for the control plane. Just to quickly introduce it. So there's a control plane namespace or system namespace, which is used to install the controllers. We have three type of CRDs introduced in Numaflow. One is called pipeline, and another one is a vertex. And the third one is called, as I mentioned, there's a component in Numaflow called ISP. So we have an ISP service controller. So this ISP service controller, today we support Redis and JetStream. So so if you want to use Numaflow and to create a pipeline, you need to create a it's a buffer service CRD object in your namespace first. And in this object, you mention what kind of ISP you want to use. For example, you want a JetStream, you give some spec of JetStream, and we're going to create a JetStream cluster in your namespace, or you want to use Redis. You either use a in-class Redis, or you want to just give some Redis configuration. You already have the Redis running somewhere. So you give this kind of CRD object to your namespace, and then we're gonna either create the service for you or use your config. And then you create a pipeline. After creating a pipeline, we're gonna start some jobs, Kubernetes job to create those ISP within the instance buffer service. And also, we're going to generate some vertex object automatically for you based on your pipeline spec, and then there's a vertex controller based on the vertex CRD object. We're going to create some pods for you, and those pods will use to talk to the ISP and do the real data processing. And there's a daemon service. It's a department created by the pipeline controller, which used to do like data mesh query or some query stuff. It's a high-level architecture. I think it's pretty easy for you guys here to understand. So I'm gonna just spend this time, very limited time on it. And I think this is all the stuff I have in the slides. I'm gonna skip all the rest slides, but there's something else I want to mention here. Is we actually, as you see, for the UDSync, you're gonna write some code to implement the interface so that can run in the pipeline. So we support some SDKs today. We have Golang, Python, and Java support today, and actually it's we didn't get bandwidth to implement other language, but it should be very easy to do that with current examples. And yeah, I should show you some of the real pipelines we're running. Hold on, let me. How can I? Okay. Yeah, okay. Let me show you some real pipelines we're running with production data. So this is a pipeline running with a real production data. Has been there for running for several months without any issue. This is a pipeline only process the map kind of logic. So you read data. This input is actually reading data from a Kafka topic, and then there are 3 data processing vertices, doing some processing, and then in the end it forward to another Kafka topic, and you can see the throughput we can achieve right now. This one is like about 11K per second. And so for Numaflow pipeline, our highest throughput we can support today is about 15K. You also can see the watermark stuff. So basically, this pause is processing the data. Now it's 10:43, right? It's, you know, they're like 1 or 2 minutes delay for data processing. Yeah, and we are working on, you know, get to reduce this kind of delay stuff. Yeah. There, I'm gonna show you another pipeline. This pipeline has some aggregation logic there. So you also read data. Oh, it also has like more than 10K TPS. Read data. I think it's also from topic, and do some filtering. This is a map operation, and then you do a fixed aggregation. I think it's windowing. Yeah, it's a group by, and it's 1 minute, you know, 1 minute aggregation, and that's you know, PBQs we used as a storage as PVC. Yeah, and this vertex is followed by another windowing operation, and then in the end write two things. Yeah, so that's some real example I'm going to show you. Okay, let me see what else I have. Yeah, some roadmaps. Today we are running, we have the 0.7 release, and for 0.8, we are doing some performance enhancement and improvement on the, especially for reduce. And then for 0.9, what we're going to do is like, we're as you can see, today we only support around 10K or 15K TPS, but that's our highest throughput we can support today. So we want to achieve higher throughput. The idea we're going to do is like we do multi-partitioning for the ISP, and we already did some POC to prove that, you know, with multi-partitioning we can achieve higher throughput. Yeah, I think that's all I have. And questions?
Thanks a lot, Derek. Yeah, any questions from anyone? I see one in the chat from Flav. Do you want to jump in, Flav, and mention or expand upon your question?
Yeah, thanks for the presentation, Derek. I'm curious, outside of the potential for a lot of integration between Numaflow and the rest of CNCF products, are there specific differences between Numaflow and a combination of PubSub and cloud events that are triggered by PubSub events?
So first of all, first of all, the Numaflow is a streaming data processing engine. The PubSub or cloud events is kind of data source, to my understanding, right? So Numaflow is, you know, so for example, you use Argo Workflows to do batch data processing, but there's no way to use Argo to do streaming data processing. And then you know, this Numaflow is mainly for, you know, streaming data processing. It's not particular for one type of event source or, you know, what type of data source. Is technically you have whatever kind of data source, you should be able to use Numaflow to do data processing. You want to, you know, do some data instrument or data analytics, and then you know, you forward data to somewhere.
Sorry, a similar question as a follow-up is how kind of Numaflow compares to other stream processing engines out there like Apache Flink? Yeah,
that's a very good question. So we are not saying we're going to compete with Flink at this time. There are a lot of gaps in at least today. For example, Flink, you know, supports very high throughput. As you can see, we only support like 10-15K TPS today, and we are trying to achieve higher throughput. That's one thing. The other thing is Flink is kind of professional data processing, which is widely used by a lot of data engineers. The reason we want to, even though, you know, even for Intuit, we have Flink support, we have, you know, some platform you know, built on top of Flink, but to use Flink, you know, first of all, Flink only supports Java or Scala, right? So you only can write your data processing job by using Java or Scala, or if you want to use Flink, you need to, you know, the process kind of complicated. You need to wrap it as a jar and upload to Flink and get it wrong, you probably you do not have lots of insight about what's happening there if there any issue. And for us, we want to do like an in cluster, everything in cluster. So for example, you have something running in your own cluster, but if you use Flink, probably you need to get it hooked to external Flink system by using some, for example, use a Kafka topic. You write data to Kafka topic and then use Flink job to read from Kafka topic, right? After Flink processing, you forward the data to another Kafka topic and then you read it back, right? So that's it has a lot of external dependency, and then we want to use Numaflow to eliminate these external dependencies so that to make all the data processing in cluster. Yeah, we're anyways, we're not saying we're gonna compete with Flink. Our focus will be real-time data analytics and data instrument stuff. And also for Numa project, we have some other projects, Numa Logic. We mainly focus on AI ops stuff. Again, feature-wise, Flink has a lot more features that we do not have. For example, data combiner, we don't support today. Okay. I'm not sure if that answers the question.
Yeah, it does. Thank you.
Yeah, I think we can add on more things like it's like an alpha version of Flink in cloud, like a Kubernetes native version.
Yeah, Flink has been there for more than 10 years.
Yeah.
Any other question?
So just I was mentioned in the chat with the Fabios, so currently the cloud function and Lambda, all the stream processing, which is providing by any cloud provider, has like some limitations, like the processing time and the resource utilization. But in Numaflow, if you use it, it won't have any limitations. Like as long as if you have your cluster has like a resource and the Vertex will process that data element with the indefinitely the timings.
If there's no more questions, and thanks everybody for listening. And if you are interested in this project, you can, this is our GitHub repository. You are always, GitHub Numa project and Numaflow, and we have some good quick start. It can actually try this out. I think it's very easy to start. We actually test it. You can get installation and running 2 pipelines down in like 10 minutes. You're gonna see, you're gonna experience all this stuff in 10 minutes. And also, if you want to contribute, yes, more welcome. Okay.
Awesome. Yeah, thanks, Eric. One question I had really quick was if you could share more about any other users, like other use cases you're seeing besides what you just shared that Intuit's using it for.
Yeah, I'll see what's the best approach I can share all this information.
Do you know off the top of your head, like any other users that are experimenting with it so far, other use cases?
Yeah, actually we have a Slack channel. You can find it in our GitHub repository, and we have some we have a use case from Toyota. They're actually, it's very interesting. They're using Numaflow to do some autopilot and navigation stuff. It's quite interesting. You can get those information from the Slack channel as well.
Cool. Yeah, I'll post the link to the Slack channel in the community Google Doc. I'll dig that up, and if anybody has it, feel free to drop it in the chat here. Well, yeah, thanks so much, Derek. That was a really great presentation. We'll be looking out for more Numaflow talks at KubeCon. But yeah, handing it off to you, Flav, for an update on Hera. take it away.
Thanks, Kalen. And Derek, again, awesome overview of Numa. Hi, everyone. Again, I'm Flav. I've been here before. I always use kind of this set of slides to provide a brief update on Hera, specifically this intro slide to remind everyone that Hera is now an Argo Workflows and Events Python SDK with its core feature and guiding principle always being and having been simplicity. And the main approach or the main selling point is that you just inject your host and token and you start delivering value through Argo Workflows and events. I have some brief updates on adoption. Last time I was here, we were on v4.2.0 with 36 contributor to 28 stars. And we went 2 versions up with some new features, and we added more contributors and just slightly more popularity. And we have 2 new maintainers, Sam and Elliot, both from Bloomberg, who have been contributing actively a lot to the new release, which is Hera v5. And that's the main thing that I would like to showcase today and give an update on. So previously I mentioned that Hera aimed to have feature parity with Argo Workflows, but it never really had that up to v4 because I think we abstracted away a bit too much and we kind of we were implicitly using templates as inline templates, and it was resulting in large YAMLs that were not kind of reproducible with Argo Workflows specifically. But now we've made some changes, and now we actually have full feature parity. So all of the objects, all of the APIs available for workflows on events are part of Hera. And in addition to that, we've changed the dev experience, and now as part of CI, we actually check that the YAML files that are generated by Hera are exactly one-to-one with Argo Workflows upstream example YAML files. And this is part of CI, it's part of the local dev experience as well, and it's documented in the contribution guidelines. Really briefly, I wanted to, really quick, workflows are more mature than events for now, just because they've been part of Hera for multiple versions, but we have upcoming changes for events to make it more compatible with other Hera objects coming from workflows, so you can put the 2 together and configure Argo events to launch specific workflows that you create via Hera. And I have the auto-generated RTD docs here, and I wanted to show you a very brief example. So now you can instantiate a workflow, and you notice that we now have we have separated out templates and actual calls of these templates into the independent steps, tasks, DAGs, HTTP, data templates, and things of that kind. So you can use all of these things, and they're auto-generated. The documentation is actually auto-generated as part of CI, so that the Hera example is actually, the YAML is also added to the same piece of documentation, and a link is added to the upstream Argo workflow example that you can see here as well. And that is the one that's actually compared, that is compared against in CI. And there are a bunch of upstream examples that are now part of the repository, and they follow a similar style of implementation in Hera, the actual YAML output, and the link to the actual documentation in the upstream Argo Workflows repository. And there are also some extra examples that are added that we're probably going to unify with the upstream one. Here's the PR, and we're still kind of working. It's still work in progress, and we're still kind of working on v5, but we're getting very close to the end, and we're primarily focused on making things even nicer than they currently are, such as you'll see this contribution from Elliot, for example, that makes templates callable, similar to how you call a very simple function in Python that you can then parameterize with the regular step or DAG task template that you normally call, that you normally have to configure in YAML, and then of course you get the same YAML output as part of the output of Hera. So previously, Hera used to use the currently published Python SDK in the Argo Workflows repository, but that is generated via OpenAPI, and the service that is actually generated is very, very hard to work with. And we wrote our own parser of the JSON OpenAPI spec of Argo Workflows and events, and it actually generates API calls that are much easier to work with and understand. And it makes it clearer about what you need to pass in, just in case you do not want to use any of the Hera objects, you just want to use the auto-generated Pydantic Hera models. So you have the flexibility to choose between the two, and the models are also accepted when you work with Hera objects. So you're not bound to use only Hera objects, you can kind of use them interchangeably with these services. And this is a similar example, it's just the one for workflows rather than the one for events. So the current plan is to release RC1 this week, and hopefully add more examples of the upstream workflow and events YAML files, hopefully officially release v5 relatively soon. And from there, we're going to work on improving support for events, so more featureization and syntactic sugar, and making it easier to define and work with events in Hera together with workflows. And then we're going to start working on Hera CD. So that means we're going to have an Argo CD client that will hopefully unify all of these different Argo ecosystem offerings into one simple Python SDK that allows you to work with everything in Argo. Of course, none of this would be possible without a lot of collaboration and community involvement and support. And I want to mention specifically Sam and Elliot were pivotal in developing most of V5, actually, and I'm very thankful for all of their help. That's all I had. Just a brief update on current Hera development and future of Hera, and I'd be, of course, excited to talk to anyone about Hera and usage at your company.
Thanks, Flav. Yeah, thanks for the update. Excited for the upcoming release. Any quick questions? I know we're at about an hour, so folks probably need to head out, but any questions for anyone? All right, awesome. Well, yeah, thanks, Flav, for the presentation. Thank you, Derek, as well. Really great to see everybody. And JM, thanks a lot for the update from Argo Helm. Hope everybody has a great rest of the week, and we'll get this recording on YouTube soon. Catch you at the contributors meetings, or next month at the next, or actually next month will be ArgoCon. So we probably won't have a community meeting here. See you at ArgoCon, either online or in person.
Thank you.
Everyone.
Thank you, guys.